In this segment, we're going to have a look at multi-level Markov chain Monte Carlo. And after some brief motivation for why you might actually want to go multi-level rather than just using plain MCMC, we're going to have a look at how this method actually works, more on an intuitive level though. And in particular, we're going to have a look at how you can use this method within MUQ2. And you'll see that this is relatively easy to do actually, because most of the heavy lifting is already being done within MUQ. So let's have a brief look at MCMC again. The basic idea is that you start from some point in your parameter space and you draw a random proposal, typically somehow in the neighborhood of this previous parameter. And whether you make this new parameter a part of your Markov chain is then determined by this ratio of the likelihood of your proposed step versus the likelihood of your current step. If it's being accepted, it becomes part of your MCMC chain. If it's being rejected, the previous step is simply copied essentially as your new step in the MCMC chain. And you can prove that if you do this all properly, then what you get is essentially a sequence of samples which behaves as if it was actually drawn from the underlying distribution pi, which of course we can typically not directly sample from. Now that's all nice, and for samples towards infinity you recover the actual distribution pi. Now here's a slight catch in any practical implementation. Evaluating the likelihood of some parameter typically means solving for some kind of a model. And that might be a three-dimensional time-dependent PDE in some of the worst cases. So clearly this is very expensive. And when you have a look at how you could sample, in this case just from a 1D Gaussian distribution, then you really see that you need quite a lot of samples to adequately recover the actual distribution that you're interested in. And as you can imagine, that gets even worse if the distribution that you're going for is not just this very nicely behaved one-dimensional Gaussian, but potentially something higher dimensional. So as I already mentioned, considering that typically each sample means a full model evaluation, possibly a PDE, that's very expensive. And in particular, in high parameter dimensions, it can very easily happen that a lot of your parameters would be rejected simply because only a very narrow subset, if you will, of your parameters would actually lead to plausible model predictions given your measurements. There's a number of ways to address that issue. One way would, of course, be to try to make your model faster. Well, of course, that's always nice, but not always possible. What you can also do is try to make your MCMC more clever. And something that you can do is actually improving the proposals of your MCMC. And there's actually an entire zoo of methods exploiting that kind of angle. One particular way which we're going to have a look at, which kind of goes a bit beyond that, is the multi-level MCMC approach. So what is multi-level Markov chain Monte Carlo? The fundamental idea is kind of related to multi-level solvers for PDEs. So what you do in those is, rather than immediately solving the hugely complex fine model that you have, you actually replace it by a very simple one. And you first do your calculations on that fine model, and then use that solution that you get here as essentially a clever starting point, or as a way to inform your solver about the general behavior of the problem before even starting to solve the actual fine problem. And that has been really sort of the breakthrough idea that led to the highly efficient PDE solvers that we have today. And a lot of very complex models would simply be impossible to solve without this approach. And of course, it's kind of intriguing to try and exploit the same kind of acceleration for statistical methods. So what we do is, rather than on the PDE side, we would, for example, coarsen our mesh or find some simpler model. In this case, what we do on the statistical side is, strictly speaking, finding another likelihood, which is, in practice, faster to evaluate. In practice, it might in fact be just building a hierarchy of differently refined measures again. That's one way to go, of course, but fundamentally it could be anything. And the main requirements are that, and that's a bit hand-wavy, but the idea is that the coarser distributions should roughly approximate the finer ones. And what you need specifically is that expected values converge over the level hierarchy and variances go down, etc. But that's something you can look up in the relevant papers. So once we have a suitable hierarchy of likelihoods coming from a suitable hierarchy of models, of course, then what we can do is representing the expected value that we want to go for of some quantity of interest on our fine model by instead a telescoping sum. And that now depends on the expected value on our coarsest model and then a series of corrections. And you can see that this really just is a regular telescoping sum, so it just adds up to what we have on the left side. And on the theoretical side, of course, you might wonder what's the point. But the reason why this provides an advantage is that in order to calculate these coarsest expected values, you only need to run very cheap models. So basically, just think of it as an MCMC chain running on a very cheap model. And these corrections here can, if the models are chosen suitably, be estimated with less and less samples the finer you go, because the underlying assumption is that the models begin to approximate the fine solution better and better. Another point that you can also gain, and I mentioned this before, is improving your proposals. Now, if you have a very high dimensional parameter space and a very complex model, then just having any proposal, mind you, proposals that are not somehow intelligently informed by the model, would likely mean that you try a lot of parameters which are going to be rejected anyways because they lead you very far away from the given measurements. However, if you first run a chain on a very coarse model, then you can assume that the samples that come out of this are kind of plausible, at least for a fine model as well, because the resulting chain has already been tested, if you will, against the coarse model. So what we do in addition to exploiting the decaying computational effort for this hierarchy is that we also actually use samples from coarser chains as proposals for finer ones. And as such, you can also show that for suitable models again, the acceptance rates of your Markov chains on finer levels is also actually going to converge towards 100%. So while on your coarsest model, you're very likely to throw away a lot of parameters simply because you just don't know any better, the finer models are then going to receive proposals which are already very, well, let's say restricted to where the mass of your distribution lies. And the result is that you can relatively quickly cover the entire distribution and have only very few samples being rejected. A bit more formally, that algorithm looks like this. So you start with a regular MCMC chain on the coarsest level, and for each subsequent level, you use actually as your proposal your previous step from the coarsest chain. If you also add more parameters on finer levels, which may be reasonable, then you can draw those from a separate fine chain proposal density as well. Now, whether we accept one of these proposals on finer levels now depends on this probability, which is a bit more complex than what we had in the standard MCMC case, but fundamentally it's still the same thing. It compares the likelihood of your proposed parameter versus the likelihood of the previous parameter, and here on the right side of this, you get an extra term which essentially corrects for the fact that your proposals are in a way biased due to coming from this coarser chain. But in this case, actually, the bias is a good thing because your proposals are very likely to be accepted. And of course, the actual expected value that you get out of this is accurate. So let's take a closer look at the internal implementation of this within MUQ. The idea is that, as we just saw, the kernel on finer levels is still just a regular Metropolis Hastings kernel plus some extra term. So it still fits perfectly within this architecture that we have in MUQ, that essentially you have a kernel, you have a separate proposer that all feeds into a chain, etc. So what the implementation does behind the scenes is setting up an entire hierarchy of Markov chains, which are essentially not too different from the implementation that we have for just regular MCMC chains. Only this time they actually receive a slightly modified kernel. And of course, proposals now don't just take your previous point and come up with a clever guess, but instead draw samples from Corsair chains as well. And as you can see, this is actually called, the components are actually called multi-index kernel, etc. And the reason is that you can extend this multi-level concept to even multi-indices. The idea being that you might have more than one way to refine a model. But we're not going to go into too much detail about this right here. Now, how do you actually use multi-level MCMC in MUQ? And note that this is both for multi-index and multi-level MCMC. The idea being that for multi-index MCMC, you, rather than building a hierarchy of models, you build an entire grid or sort of hypercube of models. And that may be relevant if there's more than one way to actually refine your model. Because the underlying implementation can be built in such a way that multi-level MCMC is simply a special case for multi-index MCMC. We also support the multi-index version here. But mostly in this talk, we're going to focus on multi-level, so don't be too surprised if instead of level indices, we actually have multi-indices for the more general case. All right, but what do you actually have to do? So what we need to provide is the posterior likelihoods that we have for each level, or in the general case, for each index. And those are simply defined as sampling problems, just like what happens in the MCMC case. And the idea is that you have to provide a log density function, which is receiving the particular parameter that it's supposed to be evaluated for. And you're supposed to return the likelihood for this parameter. And that would, for example, mean solving your PDE given this particular parameter and comparing the results to measurements in some Bayesian setting. Also, here we return the quantity of interest as a separate function, just to avoid computing the quantity of interest for rejected samples, but that's more for performance optimization. So for multi-level methods, there are a bit more things that you can actually choose freely compared to a regular MCMC method. For most of these, you can actually just use default implementations and then you get the algorithm I showed you before. But there may be certain ways in which you might want to modify this, so here are certain points where you can specify those. Most importantly, what is specific to your problem is, of course, what the actual sampling problem should be for each level. So instead of having the single sampling problem, we now have an entire hierarchy defined by this function. So you get an index or a multi-index, and you're supposed to return the sampling problem for that particular level in your hierarchy or index in your multi-index system. Further, you could specify how exactly proposals from coarse chains are being used to inform finer chains. Typically, that means just run a coarser chain, do subsampling, and every nth sample is being used as your proposal for the fine chain. And in that case, you don't have to do much. but you might be able to come up with some different approaches, and at this point you can specify all that. Finally, running the whole thing really just means pass the component factory we just defined into the existing algorithms. And just for reference, here's also a single level variant which just runs a regular MCMC chain on the finest model that you define. And that's sort of basic sanity check to see if you still achieve the same expected values. Of course, that's now losing all the advantages of multi-level, but you have a simpler reference point to ensure that you get the right results. Now let's have a look at the actual source code. So within your MUQ installation, you will find a folder examples. Within that, sampling algorithms MCMC and multi-level Gaussian. This is a very simple minimal example of running a multi-level MCMC. And instead of being based on an actual computationally intensive model, this is directly using analytical densities to sample from, particularly Gaussian densities. Those are chosen in such a way that you have one Gaussian density that we are trying to sample from eventually, and causal levels are generated by slightly shifting the expected value of these Gaussians and also increasing their variance a bit. And that mimics the behavior of typical cause models, since for one they would have a certain bias, and also considering the increased errors that you would get from your models, it also makes sense to trust the model predictions a bit less and therefore increase the variances in your posterior. When you have a look at the actual source code, it really matches what we had introduced in the slides before. So the core part of the whole thing is, as I mentioned, a sampling problem. This one is taking a specific density, these Gaussians, which we're going to define later. And what it really does is just evaluating that Gaussian density for a certain parameter, and that's it. If you have an actual PDE model or whatever your model might be, this is the point where you evaluate the model. So taking the parameter, plugging that into certain points of your PDE solver, etc. And finally, of course, in the Bayesian setting will be something like comparing your model prediction versus some measurements, for example. Also note that for our quantity of interest, we don't do any actual post-processing here as we might do in more complex cases, but rather we just return the last sampling state. So this means our quantity of interest is the actual parameter, and for our solution, we expect that the expected value of this quantity of interest should be the expected value of the finest level Gaussian that we define later on. So defining this level hierarchy is the job of this multi-index component factory. Again, this is all multi-indices. We are only going to have a look at the first components for the multi-level case. And what this does is it's supposed to return the specific sampling problem for a given level. And we do this by defining ourselves a Gaussian density with varying expected values depending on what kind of level index we currently have. So this makes sure that we have these shifted Gaussians across different levels and increasing variances. Those are being plugged into the mySamplingProblem class that we defined before, and finally returned as our sampling problem for the given index. Further, we can also specify how the coarse proposal is supposed to be handled. So that means how coarse samples are being used as proposals for final livers. And in particular, we just use the default implementation with a certain subsampling. which arrives then at the multi-level MCMC algorithm we introduced before. You might think of different approaches in certain cases. Fineness index tells the algorithm how many levels we have. So in our case, that's 3. And finally, we are also specifying a starting point. Just as an aside, the interpolation here is telling the algorithm how to augment a coarse sample by fine samples. Typically, that would just be concatenation if you add parameters for finer levels. In this example, however, we always have the exact same parameter dimension across all levels, so that's not really doing anything. Then finally, once we have set up the actual level hierarchy for our multi-level problem, we can plug that into a solver, if you will. And that means we set up an instance of our component factory. We specify a couple of parameters, so for the multi-level case, how many samples to draw, etc. And then we plug it into a multi-level MCMC implementation, and this is specifically a greedy multi-level MCMC. What that means is, instead of having a fixed number of samples that you would draw per level, this will actually start with an initial number of samples, then have a look at how the variance decays with respect to the number of samples that you have per level, and it's hashing all this together to get an indication of how many samples you would want to draw in each level. Running the actual algorithm is rather easy, and then once that is done, you can have a look at the mean quantity of interest, for example, and show that as your result. And then finally, we are also running a single level MCMC just for reference, and that one is going to take the finest model that we have, run a standard MCMC on it, and just by looking at the comparison, we can be sure that the multi-level algorithm achieves the exact same result and does not introduce any bias or anything. One thing to mention at this point is the single level MCMC can be expected to be actually faster in this case, because our model is quite simply evaluating a Gaussian density, and of course that's not exactly costly. The multi-level case really only pays off when you put in an actual model where finer levels are significantly more costly than coarser ones. Okay, now how do you compile the source code? When you go to the multi-level Gaussian folder, you can create a build directory, and then it's just the usual CMake workflow of compiling stuff. The only specialty here is that we have to tell CMake where our MUQ installation lies, since this is not a system-wide installation in my case. Otherwise, it's really just the usual CMake, then make to build the actual targets, and that's it. Now, when you actually run this particular example, what it's going to do is setting up models per level as defined. As we specified, it's going to compute 1,000 initial samples per level, and then it's going to use the greedy algorithm to determine where to compute more samples per level. And the idea being that ideally you want to do as many coarse samples as possible, fewer fine ones because they are more expensive. You can see that this greedy algorithm really picks it up quite nicely. So first of all, works mostly on the coarsest level. Once that has been exhausted, it starts to introduce samples on the finer levels. And it really, in this case, because the given error tolerance is still relatively high to make it run fast. For the example here, you can see that it only goes down to level 1. If you were to enforce a lower error indicator, then the algorithm would subsequently also go to one more level. The result is a mean quantity of interest, and as mentioned before, The quantity of interest in this case is quite simply the parameter. So what we'd expect here is the expected value of our finest Gaussian density. And that is in fact 1, 2. It's a two-dimensional Gaussian in this case. And just to be sure, we can still have a look at the single chain reference run, which achieves the exact same results, comparable accuracy in this case. So we can be reasonably sure that this multi-level algorithm works without introducing a significant bias. Alright, so now you have seen how you can quite easily use multi-level MCMC from MUQ. Where can you go from here? So one thing is you can have a closer look at the multi-index Gaussian example. The main difference here is that instead of refining our model in one way, we refine it in multiple different ways, in this case in two. And this is again mimicking the behavior of two types of model refinement by essentially shifting the expected value of the Gaussian, in this case in two different directions, depending on where you are in the multi-index model grid. Otherwise, you can see that it's really the same approach. So you set up a sampling problem. Bigger differences only occur when you actually specify what the particular model should look like, depending on the index. And otherwise, it's pretty much the same thing, and you can just plug the resulting component factory in a multi-index algorithm, run that, and what you get is essentially the analogous behavior to what we've seen in the multi-level case. Another thing you might do is, of course, modifying the actual model. So rather than evaluating a given density as our sampling problem, you could, at this point, plug in pretty much any kind of model that you can think of. Main requirement, of course, being that in your model hierarchy, coarser models provide a good approximation for finer models, at least up to a reasonable degree. Then you can expect this algorithm to work in that case as well.